Hi, everyone, and welcome to Module 2, Lesson 2 notes. We're going to talk about waves, properties of waves, do some calculations, and talk about some more scientists that were important to the atom and different things about the atom. So a little bit about waves themselves. Electromagnetic radiation, which we're going to talk about later, is energy that has wave-like behavior. So within a wave, you've got wavelength, which is the Greek symbol lambda, and that's going to be the distance between crests and crests or troughs to troughs. So on here, for some reason, it's labeled period. This is the wavelength. So you're going from the bottom to the bottom. You can go from the top to the top. That will be the wavelength. And let's change this because I don't like negative exponents. 1 meter is equal to 1 times 10 to the 9th nanometers. Okay, just so we can have it all. You put the 1 in front of the thing, that's bigger. And wavelength is typically measured in nanometers. So in some problems, you're going to have to convert from meters to nanometers. So keep that in mind. Then we have frequency, which is the Greek symbol for nu, lowercase. It's the number of waves that pass per second, measured in either waves per second or 1/seconds, which is hertz. And so you can see at this top one here is a high frequency wave. So it occurs rapidly. And then you have a low frequency wave, which does not occur nearly as much. And then the amplitude is from that midline. So where this line is here, that's drawn through the middle, to the top or to the bottom, that's going to be the amplitude. So here is the electromagnetic spectrum. So it's just different wavelengths and frequencies of waves. And so we can get everything from radio and television waves that are going to be lower frequency. So if it has a low frequency, it's going to have a high wavelength. And then the opposite's true. If it has a high frequency, it has a small wavelength. And as you can see, as you increase the frequency of these waves going towards infrared, UV, X-rays, gamma rays, it's going to get more deadly and dangerous. So, oops. And you can see there is a very small portion of the electromagnetic spectrum that is the visible light that we see. And you've got your Roy G. Biv, your rainbow of colors. And you can see each color has a different wavelength and frequency. And so it's got some of the different colors in their wavelengths there. So you can just see. And then it says a continuous spectrum is seen as light passes through a prism and is bent at different angles to separate the colors. So if you've ever seen a prism, you shine the light through and it breaks it up into the rainbow. So let's talk about some people. First off, we've got Max Planck, found that matter can gain or lose energy in very small specific amounts called quanta. So this term is going to come up a lot. It's just a small specific amount of energy. A quantum is the minimum amount of energy emitted or absorbed by an atom. We'll talk about that in a sec. And so we have an equation here. So that's the Greek symbol epsilon, but it's just energy is equal to H times nu. So that's energy. H is Planck's constant, 6.626 times 10 to the negative 34th, and the units are joules per second. Remember, energy is in units of joules, and then nu, which remember is frequency, is in units of, remember, 1/seconds. Okay, so this is an equation we're going to see and work with here in a second. And then our good pal Albert Einstein proposed that light is both wave-like and particle-like. And so we have a photon is a particle of light without a mass that has a quantum of energy. Therefore, this is important, an electron must need a specific amount of energy to leave an atom. Okay, and so we hopefully already knew that. To become an ion, you have to change the energy in order for the electrons to leave. This is the big thing right here that we're going to talk about more in a second. So it says when elements are heated, they emit specific colors that relate to the electron configuration. So we have to understand light to understand the arrangement of electrons. And you've all seen this before. Different elements giving off different colors. That's going to be a fireworks. You've all seen fireworks before, so that's the reason why, and we can go more into that in a second. But there's another equation here, C equals lambda nu. C is the speed of light, 3.00 times 10 to the 8th meters per second. And then, of course, lambda is wavelength. Typically in nanometers or meters, depends on what the problem gives you. Remember, this is frequency. And that's going to be in 1/seconds. Okay, so just something to be aware of. If you have a wavelength in nanometers, you have to turn it into meters to match your speed of light. Okay, so the atomic line spectrum, we're going to do, there's a lab, a flame test lab that shows the same thing. We can't do this on the computer, or at least do it well, so we're going to skip this. But basically what this does is you can take a special piece of equipment and you can look at a light and it breaks it up into these different distinct lines. And from those lines, you can tell the elements that are within that either compound or mixture. I'm going to have a little video on this below in the presentation. And then you can also look for the flame test lab that will be in this lesson 2 as an assignment. So, okay, here's a pretty important person, Bohr. Bohr, the name's probably familiar to you, says found that hydrogen absorbs energy, then releases it at a specific wavelength. Therefore, hydrogen atoms have quantized energy levels. So each energy level has a certain amount of energy. That's what that's saying. And so he came up with the theory of energy levels. It says that atoms absorb quantities of energy for the electrons to move to higher energy levels, called an excited state. They then return to their original level, called the ground state. By returning to the ground state, they release photons of energy, which gives us different colors of light. Now, this only works for hydrogen. It does not work for other elements, and probably bad experimentation. He only did it once for just hydrogen, and hydrogen only has one energy level, so it makes it pretty difficult. I'm gonna share a whiteboard here so I can show you what's happening. So here, nucleus, okay? These are different energy levels around the nucleus, okay? And let's say I've got an electron, an electron, electron, electron. So I have 1, 2, 3, 4, 5, 6. I have 7 electrons total. 2 in the first energy level, 1, 2, 3, 4, 5 in the second energy level. And so that's going to be nitrogen. So what happens, what Bohr said, which does work in theory. So in comes energy into the atom, and it goes into an electron. Okay, so that energy goes into the atom, strikes that electron. That electron gets excited. Okay, it's got more energy, it gets excited, and it goes here. This is called the excited state. Okay, so once it gets that energy in it, it goes to the excited state. Eventually, it'll have to go back down to where it came from, which is referred to as the ground state. When that happens, when the electron goes back down to its ground state, the energy has to go somewhere, law of conservation of energy. So that energy comes off as light that we can see, okay? So this is basically what's happening in your fireworks. So they explode, the energy goes into the electrons. When they go back down to their ground state, you see different colors. And so in the flame test lab, I'm going to have you look at different elements and see what colors they give off when those electrons are excited. This concept works in, what is it, neon lights as well. So pure neon is a red-orange color. If you have neon tubes that have different gases in them, they'll give you different colors, okay? So that's what's happening there. And that's what Bohr said, okay? And now we know that electrons don't travel in orbits around the nucleus because there's an electron cloud. But this was the model that he came up with, the planetary model, because like the nucleus is the sun, and then the electrons orbit around the nucleus like planets around the sun. Okay, and the last page here brings our two equations together. So de Broglie found that electrons have wave-like properties. Okay, we talked a little bit about that. But the important thing here is we're going to do a couple of calculations. So C equals lambda nu and E equals h nu. Remember h, 6.626 times 10 to the negative 34th joules times seconds. And what is it? C is 3.00 times 10 to the 8th meters per second. So the question number one, what is the wavelength of a wave with a frequency? So here's our frequency. We want wavelength, so I'm going to have to use this equation here for this one. So I'm just going to rearrange and to have it for wavelength. So wavelength is equal to C over nu. And so I'm going to do 3.00 times 10 to the 8th meters per second divided by 7.54 times 10 to the 20th. Hertz is, remember, 1 over seconds. When you're dividing fractions, just so we remember, meters per second, when you divide, you multiply by the reciprocal, and you'll be left with just meters. When you do this calculation, pause here if you'd like to actually try it yourself, but everyone should be making sure that they can put this stuff in your calculator, especially with these exponents. It's going to be 3.98 times 10 to the negative 13th meters. And remember, typically wavelengths is in nanometers, so I'm just going to do a quick conversion to put it into nanometers. And I'm going to write the answer right here on top. 3.98 times 10 to the negative 4th nanometers. Okay. So now we'll look at the next one. What is the frequency with energy 5.21 times 10 to the negative 15th joules? So I'm going to use the second equation, E equals h nu. And I'm going to, again, rearrange for just frequency. So frequency equals energy times Planck's constant. So that's going to be 5.21 times 10 to the negative 15th joules times 6.626 times 10 to the negative 34th joules times seconds. And then my answer, 7.86 times 10 to the 18th. And you can write hertz, you can write 1 over seconds, you can write whatever you want. Both are correct. And then the last question, what is the energy associated with radiation having a wavelength? So wavelength is this. I want energy. The only equation with wavelength gives me with speed of light and frequency. So this is a two-part question, so please pay attention to that. You have to first plug in what you know into this first equation, solve for frequency, plug frequency into your second equation, solve for energy. So frequency equals C over lambda. Okay, so 3.00 times 10 to the 8th meters per second. Divide that by the wavelength, which is in meters, so I can do this math. You just always want to make sure that your units are the same. That gives me a 7.71 times 10 to the 19th 1/seconds. And then just plug it in for energy. Energy equals 6.626 times 10 to the negative 34th joules times seconds times 7.71 times 10 to the 19th 1/seconds. Seconds will end up canceling, leaving you with just joules. And your final answer is 5.11 times 10 to the negative 14th joules. Okay. Feel free to pause, rewind, go back, look at some of the things that you may have missed. The big takeaway from this is these calculations and also what Bohr said. Okay, Bohr's model, remember we got to make sure we know every model. Bohr's model, and then the whole thing with the electrons getting excited, going to their excited state, and then releasing that energy off as light, and then going down to their ground state. You'll see more of that in the flame test lab and in the video on the line spectrum. Great, so let me know if you have any questions.